Okay, so hello and welcome to this video tutorial for E5010 Energy Engineering. So we have a very simple mass balance problem here. It states hot air at 70 degrees C, relative humidity 5.2% and flow rate of 180 kilograms per hour is used to evaporate moisture from a drying rack of vegetables, reducing the weight from, that really should say the mass from 10 kilograms to 2.8 kilograms in 5 hours at a constant rate. Calculate the exhaust air humidity ratio. So this is a very simple mass balance problem. Let's start out, as you might typically do, by drawing a mass flow diagram. So this is stuff that we've done before at level 4. Where we can say that we've got two things here. We've got air and we've got water, right? So it says hot air at 70 degrees C with relative humidity of 5.2%. That means that a portion of that hot air we can consider air, and a portion of it we can consider water. So let's kind of describe this by saying we've got M air going in, and M H2O going in. Okay. And we've got over here, we've got M air, comma out. Apologies for my handwriting as ever. M H2O, comma out. Important point. When we look at this problem and we kind of understand the system, the air that is going in is the same as the air going out, right? There's a change in the mass of water going in to the mass of water going out because some of the water leaving the system is the water that went into it, but some of it is also water that has been evaporated from the vegetables inside the drying rack. Okay. But the air in and the air out we can assume are equal. So we can say M air comma in equals M comma out. So what I'm going to do is I'm going to just rub that out and just call it M air because it's the same thing. Okay, awesome. So as I described earlier, there's two components to this water that's coming out. There's the water that went in the inlet here, and there's the water that has just been evaporated from the vegetables inside the drying rack. Let's calculate each of those components. So first we can say, let's call it H2O from veggies. Well, it states in the problem that 10 kilograms is reduced to 2.8 in the space of 5 hours. So we can say then that that is 7.2 kilograms per 5 hours, which is equal to 1.44 kilograms per hour. Okay, so that's that component. Let's say now we've got H2O from inlet. So it's described in the problem that hot air at 70 degrees C with a relative humidity of 5.2% enters the drying rack. Bear in mind that relative humidity doesn't describe the percentage of water in the air. It means something else, okay? What describes the proportion of water or water vapor really in the air is the humidity ratio. And we can determine the humidity ratio of this hot air using a psychometric chart, which I've shown here. You'd want a high temperature psychometric chart. 70 degrees C is equivalent to 158 degrees Fahrenheit. So, and notice here we have these relative humidity curves. So we understand that the relative humidity is around 5%, which is the midpoint between 6 and 4 here. So we'd go from here to here and look across, and we'd see that we have around 66, 67 grains of moisture per pound of air. And when you do the conversion on that, you find, shall I really write this out? 66, 66, I'm not going to write out grains of moisture per pound of air. I'm just going to say 66 grains of moisture per pound of air is equivalent to a 1%. A 1% ratio. Okay. Alternatively to using a chart, you could use this online calculator, which I'll link in the description. So very simple stuff. We can just input our atmospheric pressure, 101.325 kilopascals, our temperature, which is 70 degrees C, our relative humidity, which is 5.2%. I probably prefer kilogram per kilogram, right? And I calculate it and I found that it's 1%. Okay, 1.01%. Let's just call it 1%. Okay, so our humidity ratio, often described as uppercase Y, is 1%. So going back to our problem here, we can say then H2O from the inlet is equivalent to 1% of that 180 kilograms per hour stream. So let's just say 1.1 times 180, which is equal to 1.8. I didn't need to look at my notes for that, really. Okay, 1.8 kilograms per hour. And when I add them together, how should I write this? 1.44 plus 1.8 gives 3.2, 3.24 kilograms per hour. So we understand now that this is equal to 1.8. This is equal to 3.24. It's the M air that is kind of left here. We know that M air plus M H2O comma N is equivalent to 180 kilograms per hour. And we know that this is 1.8, so we can say that M air is equal to 180 minus 1.8, which is 178.2. 178.2. Yeah, my mental maths is bad. Okay, so if we're asking then for the exhaust air humidity ratio, that would just be M H2O comma out over M air. Let's give it some notation. Which is equal to, in this instance, H2O out we found is 3.24 over 178.2, which I can tell you is equal to 0.0182, which we can describe as 1.82%. Okay, So very simple problem. That's how I'd suggest going about solving it. If you have any questions or comments about that problem, please feel free to leave them in the comments. Otherwise, thank you very much for watching.